All right, everybody. In the other videos, we talked about this idea of relative dating, figuring out how old things are by comparing the age of something to something else. And we use the example of people. I'm certainly older than you are. Grandparents are older than me. A newborn baby is younger than you, and so on. And then we took a look at a lot of those block diagrams showing rock cross-sections and trying to figure out the sequence of age for the rocks and events. We talked about what are called cross-cutting relationships. Igneous intrusions have to be younger than the rocks that they cut across. Faults have to be younger than the rocks that they cut across. And those kind of ideas. Now, today what I wanted to get into was this idea of radioactive dating, which you've probably learned a little bit about. We're going to go into a lot more detail than you probably ever have before. And how we could use this idea of radioactivity to figure out what's called absolute age, how old something actually is. So with relative dating, we're just sort of making a comparison, and we're saying, well, this came first, this came second, this came third, this is older, this is younger. With absolute dating, now we're actually putting a specific age on the object, and we're saying that this is 65 million years old, or this is 2.5 billion years old. And you've probably heard of radiocarbon dating. That is a form of radioactive dating, not particularly useful in geology, though, and we'll talk about why. So let's get into it. I have a picture here up of the beginnings of this whole concept. And to really understand radioactive decay at all, we have to do a brief review of the atom, which you've learned about before. And I put this first picture up here because the beginnings of the story really go back to alchemy. Alchemists were people that experimented with chemicals and substances back in the 15, 16, and even into the 1700s. And they were sort of people that did the foundational work, the beginnings of chemistry. But the difference really is chemistry is purely based in science, and it's based on math and observation. Alchemy, people experimented with chemicals, they did some early chemistry work, but they also believed in these sort of mystical ideas. Ideas like spells and potions and things that we don't really believe in anymore. And one of the basic ideas of the alchemists was that perhaps there would be some way of turning ordinary common substances into valuable ones, like perhaps gold and silver. There really isn't a way to do that. But they did many, many experiments trying to figure out ways of turning ordinary common substances into valuable ones like gold, silver. They looked to the stars and astronomy and believed in potions, and there was this kind of spiritual, mystical element to it. So it wasn't pure science, although it was really the foundations for modern day chemistry. Here's our periodic table of the elements, of course. You've seen it many times. And one of the ideas that the alchemists really worked on was, again, trying to convert ordinary substances into valuable ones, things like gold and silver. And if we look at gold on the periodic table, it's over here. Its symbol is AU. And right next to it is the symbol Hg for mercury. And what many alchemists were trying to do at the time was to take common substances. Mercury is a fairly common substance and well known at the time period. And they would try to convert mercury into gold. We don't know of any way to do that. But it was a logical idea because elements that are near each other on the periodic table are similar. They have similar properties. So if you're trying to make gold, well, it would make sense to look to the elements that are near gold and see if there would be a way to convert it into gold, to convert those elements to gold. There really isn't a way to do it, but that's what the alchemists were attempting to do. And through that process, they accidentally discovered a lot of interesting chemistry and really laid the foundation for modern day chemistry. Now, we'll come back to the alchemists in a little bit. Their role in the story is important. And in the early 1900s, late 1800s, early 1900s, our idea of the atom really comes to fruition. Before that time period, people had an idea of the atom, they thought of the atom, and they basically just thought of the atom as spheres. circles. And the concept was basically that if we took something and cut it in half and cut it in half and cut it in half and used our imagination, eventually we have to reach a point where we just can't cut the object in half anymore. And that was really what Democritus, the ancient Greek philosopher, described as an atom. But it wasn't really until we had real technology in the 1800s and 1900s where we could really study these tiny, tiny particles we call atoms that we really learned about their structure. And you've learned about atoms in the past, probably back even in 4th and 5th grade. And this idea is not new, but just to review it for a minute, we have a nucleus in the center of the atom, and within that nucleus we have protons and neutrons. Protons have a positive charge and are represented by the green spheres. Neutrons have no charge and are represented by the blue spheres. And then outside of the atom we have our electrons, our negative charges. What determines one element from another is really the number of protons that it has in the nucleus. And again, you've learned this before, but it's probably been a while. If we look at the periodic table, well, here's the element oxygen, and here's how it would be shown on the periodic table. And we have the element symbol O, oxygen, and then we have the atomic number, number 8, and we have the atomic mass, 15.999. An atomic mass unit is a way of measuring the mass of an atom. Atoms weigh so little, it wouldn't make sense to weigh them in pounds or ounces or grams. They're just too tiny for that. So we have this special mass unit, we call it, for measuring the mass of an atom. So it's not that the atom weighs 16 grams or anything like that. An atomic mass unit is a very small amount of mass. But anyway, we have an atomic number of 8, which means that this element, oxygen, has 8 protons in its nucleus. Atoms are normally electrically neutral, and since we have 8 positive charges, 8 protons in the nucleus of the atom, it would also then stand to reason that we have to have 8 electrons too, because if the atom is normally neutral, there are exceptions to that, but that's not something we're going to get into. That's something you'll learn about in chemistry. If it's normally electrically neutral, if we have 8 positive charges, 8 protons, which is what the atomic number means, then we also have to have 8 electrons. The atomic mass is a combination of the number of protons in the nucleus and also the mass of the neutrons. The electrons are so tiny that we don't really factor in their mass when we weigh an atom. This would be a lot like if you were to weigh yourself on a bathroom scale. If you got a haircut before or after you weigh yourself, it's really not going to make a difference. A little bit of hair does not really affect your overall weight. Well, the idea is that the electrons weigh so little that we don't even bother adding them in or factoring them into the overall mass. Just like if you go get weighed at the doctor's office, they don't ask if you just had a haircut or not. It really doesn't matter. It's such a small amount of mass. But the protons and neutrons have the majority of the mass in the atom, and that's what makes up the atomic mass. These ideas will be important when we start looking at radioactivity. So if we start to think about this idea of radioactive decay, and we're really simplifying this process, and this process is actually much more involved, but we're going to just kind of do a brief overview. If we look at the nucleus of a radioactive element, like for example uranium, we can see there's a lot of protons and neutrons there. And if I go back to the periodic table for a minute, which was on one of the other slides here, most radioactive substances tend to be toward the bottom or lower part of the periodic table. Not all, but most. Radioactive elements tend to have large amounts of protons and neutrons. So lighter elements tend to not have radioactivity. We need elements with high numbers of protons and neutrons. So if we look at the top half of the periodic table, they have low atomic numbers. There's not many protons and neutrons there. But as we get toward the bottom half of the periodic table, we have much larger numbers of protons and neutrons. 107, 62, 113. These elements are radioactive. They have higher numbers of protons and neutrons. So if we go back to this diagram, here we have the element uranium, which I'm sure you've all heard of and know is radioactive. It has a large number of protons and neutrons. And the more protons and neutrons an atom has, the less stable it is, which means that the more easily some of these protons and neutrons start to come off of the nucleus. And when those protons and neutrons come off of the nucleus, they're ejected as what's called an alpha particle, which is a form of radioactive decay. When we have this particle come off the nucleus of the atom, well, this is our radioactive particle. But what it also means is we've changed the number of protons and neutrons within the element. And if we change the number of protons and neutrons within the element, it means we have a different atomic number. And if we have a different atomic number, it means we're dealing with a different element. So if we go back to the periodic table for a second again, if we have, say, some element like, oh, I don't know, uranium, for example, or thorium, or some other radioactive substance, here's uranium here with 92 protons, which also means 92 electrons most of the time. During the course of the lifespan for some uranium, some of those protons and neutrons are going to leave its nucleus. And when they do that, that means that the number, the atomic number, changes, and it's no longer 92, it's a different number on the periodic table. In fact, uranium gets converted into the element lead, which is Pb on the periodic table, which is over here. Which means that we have one element becoming another. This goes back to alchemists. Alchemists were trying to make different elements from others. And in the early days of chemistry, that was thought to be impossible. But when we discovered how radioactivity worked in the late 1800s and 1900s, early 1900s, people realized that this idea of transmutation, one element becoming another, was actually happening. In fact, the people that discovered this were actually afraid to publish their results because they were afraid of being thought of as alchemists and not as chemists. By the time we got to the 1800s and 1900s, alchemists were considered ancient history, and nobody wanted to be associated with alchemy anymore. It was thought to be impossible. And what the alchemists were trying to do is really impossible. We can't turn mercury into gold. But elements can convert from one form into another by changing the number of protons and neutrons within their nucleus. So again, if we go to uranium, uranium gives off protons and neutrons from its nucleus and breaks down into a different element, lead. Different radioactive elements will break down into different non-radioactive elements. The radioactive form we call a parent product, and the non-radioactive form, uranium breaking down into lead, lead is the non-radioactive form, and we'll talk about this more in another video, is often what's referred to as the decay, or sometimes it's referred to as the daughter product. So the basic concept is that when we have radioactive decay happening, it happens in heavier elements that have large atomic nuclei, meaning they have large numbers of neutrons and protons. The nucleus breaks down, ejects some protons, and becomes a different element. Again, the periodic table is organized by atomic number. 1, 2, 3, 4, 5, 6. Each element having one more proton in its nucleus than the one before it. And if we change the number of neutrons and protons in the nucleus, then that means that that element has become something else. So in the next video, we'll look at this in the class notes and go into more detail. So watch out for that.